Oh, it would help if I connect to this.
You made a PowerPoint Christmas
They
list.
told me, they said, go to him, they said, go to your teacher, talk to him about the Valentine's Day. They said, if you still think it's over, just do it on like a.
Okay. I will do my best to fight the diverting attention to the wonderful world of fluid mechanics today. I know how things go. I get it. But we do have some stuff to talk about today in the wonderful world of structure. So, all right, let's get started. Just a couple quick housekeeping items. So number one, your project submittal 1 has been graded. Everybody should have your grade reports on that. And then exam 2 is being graded. I would like to get that done by Friday, but it'll probably be Monday, just with registration and whatnot this week. I will do my best to get that done as quickly as possible. How did homework 7 go? How did the math hand homework go? Okay, good. One of the things I did in the last lecture is I tried to cover some things. I mean, I was always going to cover some Excel tips and tricks, but I tried to cover some things that were a bit more directly related to the project because I want to show you my schedule moving forward. And I don't know if I showed you all this the last time, so if I did, again, my apologies. I'll pull the QR code up again, but I kind of want to talk about this. This is our schedule until Thanksgiving break, okay? So just a couple housekeeping items. So we're currently in week 12. So what did we do last week? Last week we had the exam on Monday, we canceled class on Wednesday, and then we did our first mass hand lecture on Friday, and then this was the pre-recorded lecture that we did last time, okay? So today we're starting our topic on the theory of influence lines. We're going to have 5 lectures on influence lines that go through how to construct them and then how to use them. And then we go through our last topic of the semester, which is matrix analysis. So the way matrix analysis is going to work is we're going to have 2 lectures on week 14, Monday and Wednesday. I'm going to assign a homework. It's going to be due after break, but it's not going to be due until Wednesday after break. So it's not going to be due like on Monday you return. What we're going to do on Friday of Thanksgiving break is we're going to have a project troubleshooting day. And so here's my point. If the project's done, you don't have to come, okay? I'm just going to be here in case you want to come and ask questions about the project, okay? But I'm not taking attendance that day. You can come or not, okay? The link to submit project 2 or project submittal 2 is open on Blackboard, okay? And for that submission, I need 3 things. I need the AutoCAD drawing of your final truss with all the members and all that. I have an example on Blackboard for what it should look like. I want your Excel calculations or your calculations, however you choose to do them, neatly formatted and all that. Then I want your masthand file. What I want in your masthand file is the real analysis, and I want the final member selection. Because what should happen is I should run that masthand file, get a deflection, and I look at your final Excel calculations, and I should get the same deflection. Okay, so that's sort of the idea. Okay, so don't put the virtual loads on the masthand file, put the real loads on the masthand file. Real loads, final members, that deflection should match what you calculate. Sound good? Any questions on that? Okay. Ready to start talking about influence lines? Okay, I'll pull the code up one more time. Did everybody get the code? Please get the code. Okay. All right. Hurry up. We're waiting on you. Everybody wait. Okay. Did you get it?
Yeah.
Okay. All right. Okay, let's talk about the theory of influence lines. I said that influence line homeworks, at least the first couple of homeworks, like this homework 8.1, is a relatively fast homework, okay? And the construction of an influence line is a fairly fast enterprise. But I want to begin my discussion of influence lines with a disclaimer, okay? Influence lines are going to look a lot like shear diagrams and moment diagrams. They are not shear and moment diagrams, okay? I'm going to say it again. They are not shear and moment diagrams. You know what? Just for kicks, I'm going to say it a third time. They are not shear and moment diagrams. but they're going to look a lot like them. Okay. In many ways, they are essentially the inverse of a shear and moment diagram, and that'll become clear as we get into this. Okay, so what's the motivation? Up until now, what's happened is I give you a structure, I give you some loads on that structure, and you then analyze that structure, right? So what happens if I take the loads on that structure and I reposition them, if I move them? Suddenly, it becomes a whole new problem, right? I mean, even something as simple as taking this truss and deleting that load, just getting rid of it. All the reactions are different, all the method of joints analyses are different. It's a totally different problem, right? It's a really easy way for me to just take a problem and delete it, redo it, okay? If we change the position of the loads, we'd have to redo the problem start finish, okay? Moving loads or dealing with structures with moving loads does raise the possibility, or does raise two inquiries that we kind of need to address, okay? The first question is there a tool that we can develop that we can use to analyze the structure subjected to moving loads? And why would we want to do that? A bridge, right? Bridges are structures with moving loads on them, right? The vehicular loads move across the structure. So we need to be able to handle not just a structural analysis due to the loads at one position, but an analysis that results in an envelope of responses due to the loads at any position. Does that make sense, that idea? So that's the first question. But then, okay, we have this tool. Can we use this tool to do the structural analysis for us? Okay? In other words, can this tool tell us where to put the loads to generate the worst case scenario load placement? Can we get that answer directly with the influence line? And the answer is yes. Okay? That tool is called an influence line. Okay? And I want to explain what an influence line is, and then we're going to go through several examples on how to construct one. So what is an influence line? An influence line, you know, no surprise there, it is a diagram used to assess a structure subjected to loads that move. So here's how it works, okay? So what you do is you take your structure and you pick a point on the structure that you are interested in, okay? That point could be any number of things. It could be the reaction at A. It could be the shear right here, or the moment right here. Like for example, if I have a beam, right? Okay, I have a beam and I have a support here and a support here. Okay, I'm gonna have a reaction there, a reaction there. So I could say I'm going to draw an influence line for a response of interest. It could be this reaction. It could be this reaction. It could be, what is the shear if I samurai sword right here? What is the moment if I samurai sword right there? So I have to pick a point of interest, okay? And then what I do is I take that structure and I take a single unit load, so we'll say a single unit load of 1. You can think of it as like 1 kip, but really it's just, you know, a unitless 1. And we take it and we move it across the structure, okay? And then as we move it across the structure, we keep our eye fixed on that response of interest, that point of interest, and we record the response as the load moves. So on the x-axis, we put the position of the load, and on the y-axis, we put whatever response we're looking at is. And that plot is an influence line, okay? This basic definition, I want you to keep that in the back of your head, because that basic definition will help serve as a gut check to ensure that what we're doing and the graphical approach that we use still works, okay? So let's do a basic example. Okay, so I want you, we're going to do this one on the board a little bit. I've got some of this on the slide, but let's do this on the board a little bit. Okay, so let me clean up what I've got here on the board, and let's see if we can walk ourselves through this. Okay, so this is the simplest influence line example that I can think of. Okay, so I have a simply supported beam. Okay, we're going to say that this structure is 80 foot long. Okay, it's going to have a reaction here and a reaction here, right? It's also going to have a horizontal reaction, but for the purposes of influence lines, we're primarily dealing with vertical loads. So that's one thing I will mention about influence lines. is that we are primarily dealing with vertical loads because the application is for bridges, right? I mean, that's not to say you couldn't theoretically use an influence line for incline loads, but we're talking about traffic moving over a bridge. That's why we primarily discuss that. Okay? And we'll call this support A, we'll call this support B, and I want to figure out, put this right here, I want to draw a diagram, and we'll draw the influence line for, let me redo that, the influence line for AY, okay? So in other words, I want to figure out what does the influence line for AY look like as we move the load across the structure, okay? So we'll put a coordinate system up here so that we can sort of track this, okay? So let's put some systematic stuff to this. Okay, let me ask you a question. What would the reaction at A be? So this is AY, this is BY, okay? So I want you to keep your eye fixed on this. This is what I want you to pay attention to. Is that right there? Okay? I want to ask you a question. If I put this load right smack dab in the middle of the beam, what is the reaction at A?
The reaction at B.
What's that?
The same as the reaction at B.
And how much?
0.5.
0.5. Okay, so here's what we'll do. We'll make ourselves a little table. Okay, and we'll say something like at x equals 40, this is a half. Is everybody okay with that? Okay, so what I'll do here on the influence line is right here, I will put a point there, and I'll say that's 1/2. Okay, does that make sense? And if you're not with me, just bear with me. Help me out with something. What if? Okay, now keep in mind this one kip load moves. Okay, so I'm going to put it somewhere else. Okay, I'm going to take this and I'm going to put it right there. You made it. Studying for fluid pressure related exams. I get it. All right, so I have the load right here, okay? Now, again, whenever you're doing an influence line, you keep your eye fixed on the point of interest. So my question for you is, if I put the load right here at B, what is this reaction? 0, okay? So if I'm writing this in a table, would I say at 80 feet, this is 0? So that's going to be right there, right? Everybody with me on that? Okay, let's do this. Okay, now let's put the load right there. If I put the load there, what's the reaction at A? 1. So this is x equals 0 feet, 1.0, right? So that's going to look something like that, right? So I propose that the influence line for the reaction at A looks like that. Okay, does that make sense? That's what we get. So boom, you drew your first influence line. Congratulations. Okay? There is a lot packaged into an influence line. It is an incredibly deceptive but incredibly effective tool. Like it's deceptive how effective it is because it seems super basic. And it is, but what you can get out of this is amazing. And you're going to see this throughout the next few lectures. Okay? Let me sort of explain a couple points. For example, okay, if I had a moving load and I was a geotechnical engineer, my responsibility was to design the foundation under support A. Where would I put those loads to generate the worst case response for design? I'd stick them over here, right? Because this is where the highest values on the influence line is. With me so far? Okay, here's another application. You told me that if I put the load right in the middle, the reaction is a half. Why is the reaction 1/2? I would say because the load is 1. What if I put a 14 kip load in the middle? What would the reaction be at A?
7.
Now, how did you do that? How about a way of doing that is 14 times a half? So here's my point. Let me say it like this. If you draw an influence line, which is the response due to a load of 1, you can determine the response due to any magnitude of load anywhere. You see what I mean? That's sort of what I'm getting at. Okay? Now, I bet money that everybody in here is already starting to get a little bit of a feel for what influence lines look like. And I'm going to test that by asking you, what does that look like?
The opposite.
It's going the other way, right? It's going to look like this. Right? Let me show you a couple other gut checks. I want to look value for value. Is this 1/2 and that 0? So how about in between? What's this value going to be up here? 3/4. What about the value down here? And same thing like right here?
1/4.
And 3/4? Watch this. What is this plus this right here?
1.
What about that?
1. 1. 1. 1.
Why is that the case? And I propose that happens if you draw the influence lines for every reaction in a structure and superimpose them. That will always happen. Why? Because the sum of the forces in the y direction equals 0. I have a 1 going down, so I have to have 1 going up. Does that make sense? There's a lot baked into this. Okay? So far, so good? Okay, now, a couple things. This is a fine way of learning how to understand influence lines, but it is really tedious. Remember when we were doing shear and moment diagrams and we said we could just cut sections and plot it, and that would be a pain. We said, let's not do that. Let's develop a graphical approach. Let's say, let's develop some patterns, and then we can draw shear and moment diagrams more effectively. Okay, well, we're going to do that here as well. Okay, influence lines. So a couple things. Influence lines for statically determinate structures are always linear, always. Okay, and you're going to kind of understand why here in a bit. Okay, for indeterminate structures, that might not be the case. And again, you'll bear with me, but you'll understand why here in a bit. Now, how do we prove this? Or, again, maybe I'm dancing around this a bit. Maybe how do we develop this approach to generate arbitrary influence lines? Okay. Is there a more straightforward approach? The answer is yes, and the name for this approach is called the Müller-Breslau principle. Okay. Now, the Müller-Breslau principle is a mouthful, but once you work it through in your head, you'll see how easy this is. Okay. So this is, if you were to define the Müller-Breslau principle, this is what the Müller-Breslau principle says. It says the deflected shape of a structure represents, to some scale, the influence line. Specifically, the influence line for a given force effect, if you take that force effect and you move it through a small displacement. I am sure, given the fact that everybody's thinking about non-Newtonian fluids right now, that you're going, what? That was a lot. What are you talking about, Dr. Mike? So I'm going to distill this for you in a real easy to digest step by step. Okay, so here's how an influence line works. And this is how the Müller-Breslau principle works, I should say. So the first thing that you do is, just like over here, you identify a response of interest. What are you drawing the influence line for? So what we'll do is we'll say, let's just say that we are drawing the influence line for the reaction at A. Okay? Then what we do is we take that support reaction and we kick it away. We get rid of it. Okay? And then we take that structure and move it through a unit displacement. And the resulting deformation is the influence line. Let me sort of walk it through over here. Okay. So, can I erase some of this? Okay. Ignore all this influence line hullabaloo, and I want you to just look at this structure. This structure is determinant, right? This is a statically determinate structure. I sub E equals 0. Okay. Now, what does this say? Identify a response of interest. So let's say we've identified the response right here. And then what I'm going to do is I'm going to kick that support out from under the beam. So I'm going to take the beam and I'm going to turn it into that. What can you remark about this beam?
It's not statically determined.
Well, it's not.
It's statically unstable.
It's not stable. This isn't a stable structure. Unstable structures don't deform or bend. They just fall over, right? Here's an unstable structure. It doesn't curve, right? It doesn't, bend like that. Okay? So what I'm then going to do is I'm going to pick this point on the structure and I'm going to move it up. So much so that that displacement is 1. Now if I pick the structure up and I move it up 1, what does that look like? Well, it looks like this, okay? So here's the structure, and if I pick that point and move it up, that's what it looks like, right? It just whoop, goes up, right? Isn't that resulting displaced shape the influence line? Isn't that what it looked like? That's what the Müller-Breslau principle states, and that's the graphical approach that we're going to use, that we just pick the structure up and we deform it. Okay? With me so far? We can do this for some really interesting and complicated structures. Okay, so let's take a look at what I've got here on the slide, because I'm gonna go back and show you these here in a bit. But now I have a influence line situation that's a little bit more involved. Okay, so let's say I'm trying to draw the influence line for the reaction at A. Okay, so let's just take what we know about structural behavior and let's make some common sense observations. If I put the load at A, what is the reaction at A?
The load.
Which is, in this case, the load is 1, right? So I'm saying that right here, that needs to be 1. Are we okay with that? If I take the load and put it at B, what is the reaction at A? No, hold on. It's 0, right? If you put the load right here at B, the reaction at B is at 1. Here it's 0, right? So this should be 0. What about if I put the load at C?
Still
0. In fact, would a general statement about reaction influence lines be that influence lines for reactions should equal 1 at that reaction and 0 at all other reactions? Right? Is that just common sense? Does that make sense? Okay. We said influence lines are lines. Okay. So I propose what's going to happen is the following. Okay. So here's what I propose is going to happen. You stop. So here's that structure. Okay. I don't know how easy that's being visible, but here I've got support A, support B, support C. Okay. If I take support A and lift it up 1, so here's what I'm doing for this structure. Okay. So let's draw this structure out. Okay. So here's the structure. All right. So I have a support here, support here, support here, and then I have a hinge right there. Okay, there's a hinge right there. What I'm doing is I am removing that support and I'm picking this up 1, right? But I'm not getting rid of this support and I'm not getting rid of this support. So I'm sort of saying the structure from here to here is going to behave like a seesaw, right? And then this hinge, it's going to do that. So if I look at the structure as it deforms, it does something that's kind of like this, right? The hinge right here is where it sort of like changes direction and it pivots about where the supports are, right? Not only does that make sense kinematically, but it makes sense from a structural response standpoint, right? The influence line has got to equal 1 here, 0 here, 0 here. And it also has to be linear. The influence lines are lines. Make sense? This is the only way that those facts can be satisfied. Okay? So far so good? All right. So if you were to look at the entire structure, and you can see it all right here, but again, what do we know about influence lines? Influence lines equal 1 at the reaction of interest and 0 at all other reactions. They're always linear for determinate structures, and you'll see what I do with the linear here in a bit. And the internal hinges change the direction or change the slope of the line. So this is what the influence lines look like for this structure, okay? So let's take, for example, the influence line at B. It's 0 at A, 1 at B, 0 at C. So what would we do for the influence line for the reaction at B? So here's the structure. Get rid of that support and then pick this point up. Well, think about this. This is a hinge. In order to pick this up, this has got to go up, and then that's got to go back down. Does that make sense? Everybody kind of see that over here? Go with me on that? So how do I get the numbers? Well, the numbers are just slope ratios. Like if I look at AY, I've got 1 in 12. So how far do I go in 6? A half, or negative a half. Same thing here with BY. I go 1 in 12, so in 18, I go 1 and a half. And as for CY, so if I look at CY, the deal with CY is I have a roller here, so this is the original structure, and I'm getting rid of this and picking this point up. Well, the only way that happens is just to pick that little bit up, right? And what do we have? This plus this is 1. This plus this is 1. Negative a half plus 1 and a half plus 0 is 1. That plus that is 1. Does that make sense? You want to do some practice? Let's do some practice. Okay, so I want to, before we get into the notebook here, I want to show you what I've got here in these slides. So I've got influence line example 1A, and then I have influence line example 2A, okay? So I've got two different structures, and the reason I'm calling them 1A and 2A is because next time we're going to go back to these structures and look at them again, okay? So, for example, for 2A, we're going to draw the influence line for each of the vertical reactions. There's this section here. We're going to ignore that. Not that we're going to totally ignore it, because we're going to come back next time and redo it, okay? I'm just saying, for this time, this isn't going to matter. So far, so good? All right. All right, so let me pull up the notebook here. Okay. So here's my diagram that I drew, and I have the influence lines right here. So I drew these sort of vertical lines to sort of give myself a guideline to go for. And then I've got two spaces where I'm actually going to draw the influence lines. So again, all we're doing now is influence lines for reactions. Okay? So we're going to have the influence line for AY and the influence line for CY. Okay? So let's see if we can work through this. For AY, what's the value here? 1, right? What's the value here?
0.
0. Okay, now let me ask this question. How many total physical pieces are there on this structure? It's just one solid beam from A to D, right? Okay, so I propose the influence line is going to be one solid line. Okay, Because if I take the roller at A, or the support at A, remove it, pick it up one, it's going to be like a seesaw where this is the fulcrum of the seesaw, right? So the influence line for the reaction at A is going to look like that. Okay? This is 0. This is 1. By the way, what is, I'll do this in another color. What's that value? Wait, tell me what that value is. Say it again. 0.3. Well, is it 0.3 or more, like in a fraction? 1/3, yeah. 0.3 repeating. What about that point? -1/3. Do I need to go through the math on that, or is everybody able to just sort of observe that based on the linear pattern, that's 1/3 and a -1/3? Okay? All right, I did AY. I want somebody in here to tell me what CY looks like. I'm not telling you, you tell me. 0 at A. 1 at C. So what you're saying is it's just going to, boom. You're 100% right. Oh, I wanted to do that in blue. And so you said this right here is 4/3. So, by the way, what is that? 2/3. Okay. So far, so good. And by the way, let's do a quick check, okay? Let's consider the load at D, okay? So what I'm saying is let's just put the load right there. And let's just ignore all this influence line hullabaloo. Let's just treat this like this was a problem in the wonderful world of structural analysis. So this dimension right here, what is this dimension? This is 30 feet, right? And that's 10 feet. Is that right? Okay. So this is A. This is C. So what? All right. So let's sum moments at A. So what do I have? 1 times 40, right? And so I got to have something times 30. So we'll say that CY, what was I doing? We'll put CY like that. So we'll say, was that 1 times 40 feet? Like that. So we'll get CY is 4/3 going up. Is that right? So, by the way, help me out. If I sum forces in the y direction, what do I have? I've got 1 going down, and I've got CY is 4/3 going up. something's imbalanced. I need something going down, don't I? Like it doesn't work out. I need an AY going down. So we'll say 4/3 is AY plus 1. So therefore, AY is 1/3 going down. Is that like what we got? What do we have? A positive 4/3, so we'll say vertical reactions upward, positive 4/3 going up, 1/3, negative 1/3, 1/3 going down. You see what I mean? And hopefully you're starting to see that, okay, think about it like this. I just drew a picture, and now I figured out the reaction anywhere on the beam, with the load anywhere on the beam. You see what I mean? You can do structural analysis really fast with influence lines, really fast. So far so good? All right, any questions on this? Okay. Okay, so this one's a little bit more involved. So I'll give you all a sec to copy this one down, but what I have here is I have 3 supports, right? So we're going to do 3 influence lines. So we're going to do the influence line for AY, BY, CY. And by the way, I am very sorry, but I forgot something I wanted to point out on the last problem. What is this plus this? This plus this? This plus this? That plus that? It's still 1, right? So, okay, sorry. I couldn't help myself. Okay. Okay. All right, let's see what we can see here. So let's take it one at a time. Let's start with AY. What is the value right here? 1, 0, 0, right? Okay. Okay. Now, I want y'all to look at this structure. I want you to think real long and hard about what the influence line looks like. And just to give us something to look at, we'll call this point C and, point D. And if you want, we can call this point E, although, I'll probably just call it a section later. But, okay. The big thing I want you to recognize is that there's a hinge at D. That's a hinge, okay? So I want you to think long and hard and tell me, can somebody describe to me what they think the influence line for AY is going to look like?
It goes from 1 to 0, from A to the hinge, and then 0 the rest of the way across.
You are 100% correct. That's what it looks like. Because, see, B and C are still pinning it down. Think of B and C as like little clamps fixing that thing down. That's the influence line. That's it. And so this is a really interesting observation. So I want you to think about this result in an entirely different fashion, okay? Think about this structure. Before today, think about this question. I'm going to put a bunch of loads on the beam. What's the reaction at A for all those red loads I put on the beam? What's the reaction at A if I put all these loads on the beam? 0, right? No load on this side of the hinge is going to cause a reaction at A. Because that's what this says, right? You never would have thought about that before, would you? See what I mean? So you, again, influence lines are really powerful. You could do a lot of damage with them. And you could start to see how, like, one of the applications of influence lines is just going to be to just do the structural analysis. Just do it with these. Okay. All right, let's do BY. Okay. Let's see what we can see. All right, so what's it going to be at A? And at C, and at B. Okay. So I'm getting rid of this hinge, I'm getting rid of this support, and I am lifting it up. But it's still pinned right here. So think, it's pinned right here. I'm lifting this up. It's got to be straight lines, and I've got a hinge right here. Somebody tell me what the deformed shape looks like. What's that? The high point's at the hinge, right? It's just whoop, high point at the hinge. 100% right. So now what? Now it begs the question: what is that high point? Hold on. So this one we are going to evaluate, but somebody said 1.4, and I think you're onto something. So what I'll do is, again, I'll use red to sort of indicate these are the ones that we kind of need to figure out. Okay. So what I'll do is I'll call this H1, H2, okay? So here's what I'll do for H1. I'll say 1.0 is to 20 as H1 is to what? 28. As somebody said, 1.4. Okay, now let me put H2 like this. So for this one, what we'll say is 1.0 is to 20 as H2 is to what? 6. So that's going to be 0.3. Does that make sense? Okay. That's not too bad, right? So maybe what I'll do is sort of move that down a little bit so you can see where that's coming from. Now, does anybody have a little cheat code on maybe how we can get the influence line for the reaction at C? Will you say it again? Exactly. It's got to add up to 1, right? So what does this value have to be? 0. Now there's two ways of figuring that out. One, it's a support other than C, but 1 plus that plus, it's got to be 0, right? Okay. So let's just go ahead and say this is 0. This has got to be negative 0.4, right? This has got to be 0, and over on the right, it's got to be 1, right? So what's got to happen is it's got to go down, then through like that, right? And that's kind of what it's got to do, right? Because the hinge is going to change the direction, but it's still pinned here and pinned here. So it's going to... Ooh. So this is 1, 0, and then we have a point here and here that we have to figure out. But again, we don't really need to do any figuring it out because we know that, and that. Because it's got to sum up to be 1. That has to be negative 0.4, and that has to be 0.7. Okay? How are we doing? So far, so good? Now, hopefully, we're getting ready to end on time, but I'll say this. Hopefully, you are starting to see not only like that these are pretty easy to construct once you understand the pattern, but I'm hoping I'm giving you a little bit of a peer into using these things to actually do some real world structural analysis. That it's not just some weird picture that Dr. Mike's put on board, that there's a reason for it, okay? Everybody good? Any questions? Yes?
Just kind of clarifying question. So if I wanted to take these graphs and turn them into a reaction at somewhere, I would just take the net forces going out in the y direction and multiply it by whichever point in that graph.
Yeah, and I'm going to give you one more, okay? So if I wanted to find the reaction at B due to a bunch of loads, right? I would just take load times associated value, load times associated value, load times associated value. If it was a distributed load, I would take the distributed load times, what do you think I'm going to say? The area under the influence line where the load is. And don't worry, we're going to do that next week. We're actually going to explicitly do what you're talking about next week. So, sound good? All right, I'm going to pull up the code one more time. I will see you all next time.